Okay, so now we're moving on to part 2 of this lesson. We talked about the difference between a population value and a sample value. Now what we're going to investigate is what the distribution of your sample would look like compared to what the distribution of your population would look like. So a sampling distribution shows the statistics found in all possible samples. So it shows the statistic found in all possible samples of size n. The key word here when you get questions about sampling distribution is this idea of all possible samples. And we're going to investigate this further, but the biggest indication that you're talking about a sampling distribution is this idea of all the possible samples. Well, the population distribution just shows all the people in the population. So this is all individuals. All individuals. We're going to use a very small, made-up data set to investigate this. So what we're going to look at first today is the sampling distribution for a mean. And I want you guys to highlight that because back on this page, you can just circle it or mark it any way you want. Back on this page, we have two common things that we're going to estimate. We're going to estimate the average and we're going to estimate the proportion, or we're going to estimate mu and a percent. This is just, yay, thank you, dear. This is just for the average. So next time we'll talk about the proportion. So let's say that I have a stats class with only 4 students. It's getting that way. My 3B has 9 kiddos in it. So their chapter 5 test scores are 60, 70, 80, 90. Let's make a dot plot of the population distribution. So we're going to graph every single person in the population. So I'm just going to start at 50. 60, 70, 80, 90, 100. I really should have left room to label my axes. Chapter 5 test score. I planned poorly and I didn't want to erase. Okay, well, we only have 4 dots that we need to put on this dot plot. We have somebody that scored 60, 70, 80, 90. Very boring distribution. A uniform distribution. So now, let's take a sample of 2 students. So we're going to randomly select or just choose 2 students, and we want to find their mean. So we're going to say X bar equals, you're going to add the 2 student scores, and then you're going to divide by 2. So I want you to do this. You choose any 2 that you want, find the average, and then write that on your whiteboard. You choose any 2 you want, find the mean, then write that mean on your whiteboard. Give you roughly 30. Any 2, so just choose 2 of the test scores. whiteboard. Adam, divide by 2. Write it on your whiteboard. If you don't got your whiteboard, then you literally take your dry erase marker and write it on the tabletop. You can write just the answer if you want, but we'll write 20. Or roughly 10. Five. 3. 2. Okay, you guys show me what you got. Keep it up for just a second. Okay, so keep it up, but I want to tell you some of the numbers that I'm seeing. 75, 70, 80, 65. Okay, you can put them down. So, how is it that we didn't all get the same value? Well, I chose 70 and 80, and I got an average score for 2 students of 75. So what I've done here is taken a population, and I want to estimate the average score on this test by looking at only 2 students. And my estimate would tell me, okay, so for the entire class, kids got about 75 on their test. But then Brinley got, for her estimate, that the class was at 65, and Callie got that it was at 70. So this occurrence of getting a different value for your statistic is called sampling variability, and that's what goes in this part of the bubble to the right. Sampling variability. So this is the natural tendency of, I think that's the word different, but I want to make sure. This is random samples to differ from one another. It is not an error. It's just a natural result of random sampling. And I think this idea would make sense to you. No 2 groups of people are ever going to be exactly the same. So I take a group of 2 students and get 75, but if I took a different group of 2 students, I'm probably not going to get 75. This is called sampling variability, and it's okay. In a sample like this, it's way more noticeable than it normally is. We're never taking a population of 5 and only looking at 2 people. So just know that sampling variability is a thing, and it's an okay thing to see. So now it says, well, let's find all possible samples of size 2 and calculate the mean for each of them. I'm going to show you very quickly a visual of how I like to do this. So, because you're going to get a problem on your Can You Do where you have to do this. If they're asking you to combine 3 things, find all the ways you can combine these 3 things. I always start with the first and then pair it with the second. Then I go back to the first and pair it with the third. These are all the combinations for A. Now I go to B and pair it with the one in front of it. That is BC. And those are all the possible combinations. So AB is the same as BA. We wouldn't count that twice. AC and CA are the same. BC and CB would be the same. So when they want me to find all the possible samples of size 2, that's how I'm going to do it. I'm going to start at 60, and I'm going to pair it with 70. So I'm going to say 60 plus 70 divided by 2 gives a mean of 65. So this is an X bar of 65. Then I'm going to go back to 60 and pair it with 80. So 60, and you can write it like this if you want. 60 and 80 gives an X bar of 70. Is that true? Okay, then back to 60. The next one I would pair it with is 90. What's that X bar? 75. So we got 65, 70, 75. 60s are done. I've found all of the pairs with 60. So now I'm going to move up to 70. And I'm going to pair 70 and 80. What's that X bar? 75. Go back to 70, and I'm going to now pair it with 90. I'm seeing a pattern, so I'm thinking that one's going to be 80. Yep. And then the last one is pairing 80 and 90. That gives us 85 as our sample mean. Okay, so these are all of the possible samples of size 2. From this population up here, where n equals 5, these are all of the samples that we could get if n equals 2. So everybody should have gotten one of these numbers. Or I guess I should say the number you got should be in this list. Now we want to make a dot plot of these means. So I'm going to do the same scale. This time I'm going to remember to leave room for my axes. I'm going to start at 50, 60, 70, 80, 90, 100. And then I'm going to put a dot at 65, 70, 75. Oh, 2 dots at 75. 80, 85. Hola. Okay, so what we have here is our, these are all of our X bars from samples of n equals 2. So these are not actual test scores anymore. On our population distribution, what we graphed was the actual test score of each student in the class. These are not actual test scores. These are the averages from 2 students. This is a sampling distribution. This is a sampling distribution. It is showing you the X bar for all possible samples of size 2. Sampling distribution shows you the statistic from all of your samples. So now I'm going to revisit this guy and make sure that I'm clear that this is our population distribution. They look different, and that's okay, because they're not graphing the same thing. They are related, but they're not graphing the same exact thing. So population shows you every student in the class. Sampling distribution shows you the average of all of our samples of size 2. Are you hanging in there a little bit? Okay, so last question. Well, what is the true mean of the population? What is mu? Because we found a bunch of X bars, but what actually is mu? So luckily, this population, why did I say 5? This is 4. My bad, guys. Were you guys scared to tell me? Anissa, were you scared to tell me it's 4? Okay, so down here, we do 60 plus 70 plus 80 plus 90, all over 4. What does that guy equal? 75? Somebody will double check it for us, I think. Yeah. So this last instruction here says, label this on the dot plot above. Well, interestingly enough, the true mu is the center of this distribution. The true value of the parameter is at the center of your sampling distribution. That's nice. That worked out nicely for us. So true mu ended up being the center. So I highlighted it and then I just wrote mu right at the top. So this is a very, very basic example of population distribution versus sampling distribution. Now, let's make it a little bit more realistic. So that's this is our last page for the day. In reality, all of my classes have more than 4 students. So we're going to find sample means again, but this time using real class data. So we want to use our calculator to take a random sample of 5 students, record their scores, and find the mean. So I'm going to show you how to do this, and I'm going to write the buttons right here. So we are going to go to math in our calculators. So math is under the green button. And we're going to arrow over to probability, PRB. We want to choose random integers with no repeat. You want random integer, no repeat, because we don't want to get 2 of the same student in our sample. So we're going to hit enter. If you have the older calculator, this is what you type in. You're going to type in the lowest number of your students, so 1. We want a random number from 1, comma, your comma's above the 7, to 28. And then I believe you hit enter. So here's the tricky thing about these older calculators. In order to get your 5 numbers or your sample, if you need to see the other numbers, you have to arrow over immediately after you hit enter, or it won't let you look at all your numbers for some reason. So like if I hit enter and try to go back up and see these numbers, it won't show me any of the numbers anymore. So hopefully you're getting different numbers than me. Are you? Okay, so let me show you what this looks like. My first one that I got was student 19. So I'm just going to mark him. He had a score of 55. Student 11 had a score of 50. Student 25 had a score of 66. Student 9, 76. Student 16 got 98. So now I'm going to add those 5 numbers. Divide by 5. And my first sample mean is 69 for the 5 students that I got. Then I'm going to do it again. So I'm going to run another sample. So I would go to Math, arrow over to Prob, choose option 8 on the older calculator, and then enter in the same exact numbers that you did before. 1, 28, enter. If you have the newer calculator, it actually lets you enter in your sample size and just gives you the 5. So button sequence is the same. We do Math, Prob, 8, but you would type in 128, sample size of 5, and it'll just give you the 5 numbers. So you're doing that 4 times, and then once you're done, I want you to write your 4 sample means on your whiteboard so I can see what you're getting. So you need 4 different samples. You'll write them on your whiteboard. I'm going to write mine down and then walk around, so if you need me, I'm there to help you. You need at least another minute. Remember, write your 4 numbers on your whiteboard for me so I can see what you got. Do you need a marker too? Okay, let's go about 30 seconds. Roughly 20. About 10. If you haven't already, write down your values. 5, 3, 2. Okay, show me what you guys have. Good. So if you got a decimal, I want you to round it to the nearest whole. So if it's 4 or below, like I got 78.4, I'm going to round this to 78. If you got 78.6, you're going to round up to 79. Okay, so now it says, let's make, holy moly, let's make a dot plot of all of the sample means that we just found. So we're doing this right here, but now we have way more dots to put on. So I'm going to start at 65. Oh, I didn't leave enough room to label. And we're gonna have numbers in between this time. So you're gonna wanna leave a little bit of room because you're gonna need the tick marks in between. Like you're gonna need a 66, 67, 68, 69. Okay, so there's mine. I'm gonna give you at least 45 more seconds to get yours because I know it takes a minute. I labeled my x-axis. I'll come visit to see how. So roughly 30. About 20. About 10. Okay, so we are going to plot everybody's values. So we can start with mine. Mine was 69, 78, 79, 76. Okay, Callie, what are yours? 69, 67, 79, 76. Okay, Yuritsa? 75, 82, 67, 72. Shelby? 69, 82, 69, and 80. Kyler? 60. Outlier. Disaster time.
87.
Oh, wait. Kyler. I gotta drop my 60. Did you guys get your 60? I had to add them on. You guys Gucci? Did you get your 60? Thanks. Thanks. Only one that'll let me know. Okay, Kyler, I'm ready. 60. 87. 75. 73. Okay, Emily. 60. 87. 75. 72. Brinley? 71. 75. 79. And 85. Kenneth? 60. 87. 75. Say it one more time. 73. Litzy? 60. 87. Ooh, 95. 73. Zach? Oh, shoot. Probably heard you wrong. 95 is really 75. Okay, Zach. Okay.
84.
Oh, sorry. Zach said 75, 84, 81, 83. Anissa? 71. 71. What? 71. 64. Mildred? Do you want me to come back to you? Okay. Mason? 74. 63. 69. And 84. Jay? 75. 73. 82. And 70. Carter? 69. 80. 83. And 98. 1, 2, 3. Zion? Okay. Sorry, he said 69, 81, 70, and 74. Okay, let's add a few. Well, do I? No, we can leave it like this. So I think this 98 might be an outlier. Mildred, did you get yours? Okay, last set. 70? Okay. 78, 75, and 72. Okay. Okay, so let's count how many samples we took. So remember, our sample size is 5, but how many samples did we just plot? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 4 times 16. Is that 64? Is anybody checking? Thank you. Okay, we just graphed 64 samples of size 5. 64 samples of size 5. So the next question is, well, what do we think this chapter 5 test average is? Well, we can calculate it, and we will, but if we're following what we got last time, I'm going to estimate that it's probably the center of this distribution. So I'm going to find the median. So I'm looking for between 32 and 33. So I'm going to count really quick. So I'm definitely getting a center of 75. Did anybody double check me? So we think it's probably the center of our distribution so our median was 75, so we're estimating that mu is 75. We're estimating that mu is 75, just based off of our last example. Our last example, the center and the real number matched up. So if we had to estimate this, I would estimate it at the center. Now, luckily, 28 test scores is not, it's not unreasonable to average that. So if we plug that into our calculator, the true mu is actually 78. So if you plug all 28 of those values in, the true one is 78. So we're pretty close. Our estimate is pretty close. So 2 more questions. A sampling distribution shows the means calculated from all of the possible samples of size 5 from this population. Is this dot plot a sampling distribution? What do you guys think? Is this dot plot, is our dot plot, our 64 samples of size 5, is that the sampling distribution? Did we find all of the possible samples of size 5? No. No, we did not. So no. I think I have good wording for this somewhere. We didn't find all possible samples of 5 students. Now, I think I might blow your mind a little bit. So in the previous example, we had a population of 5. We chose sample size of 2, and there were only, how many? 6 different combinations. Well, for this one, the number of combinations is this area of mathematics called combinatorics. So there are, and this is how you write it, 30, not 30. There are 28, choose 5. So what this means is, how many combinations of 5 things can we take from a group of 28? There's a button in your calculator for this. Let me see if I can find it really quick. Does anybody know how you get to like your catalog that lists things? Nope. I could find it, but I don't want to waste your time. Maybe I will on my own and then show you. There is a calculator button for this, and you type it into your calculator exactly like this. And what you find is that there are 142,506 possible samples of n equals 5 from a population where n equals 28. So if that notation confuses you, you're okay, because that's not the heart of the matter. That's not the heart of this lesson. But this is shorthand for saying I took a sample of 5 from 28 possible options in the population. So is it going to be realistic for us to actually find the sampling distribution of just 28 test scores? No. The reason that we do this, though, is 1, to practice it more, but 2, also try to help solidify this idea that a true sampling distribution is all of the possible samples of that size. Okay, we're on the very last question. We took a random sample. 5 chapter test scores from Hunter High. I think that's supposed to say we took a random sample of 5 chapter test scores from Hunter and got that their mean is 68. Is this convincing evidence that Hunter High students did worse than students at our school? So we got an average of 78. We take the same test from Hunter. We find 5 of their students. We find their average, and they get 68. Is that sample average enough to serve as convincing evidence that they did worse than we did? Whenever you're asked about convincing evidence, we're looking for a certain percentage. Do you guys remember what it is? 5%. So let's look at our sampling distribution. Well, we took 64 samples from our class, and of those 64 samples, how many of them were 68 or less? So 65, 66, 67. So here is X bar less than or equal to 68. This is the section. So how many is that? 8. Okay, well, that's not unreasonable. Out of 64 samples, 8 times we got scores that were 68 or lower. So what percent is that? 12%. So if 5% is our cutoff, it has to happen less than 5% of the time to be convincing evidence. We don't have convincing evidence. They could have done just as well as we did, because we know that our true mean is 78, and yet 12% of our samples had a sample mean of 68 or lower. So maybe we just happened to get one of the samples where we had a group of kids that scored lower. Does that make sense, what I'm saying? Are you sure? Okay, so let me show you how you would write this out for an answer. So the claim, well, let's not go that far. Let's just say, no, this is not convincing evidence. Then we want to reference how we came to that conclusion. Based off of, or based on, our distribution, the percent of times that our samples had a mean less than or equal to 68, so I'm using math symbols to say that, based off of our dot plot, or based off of our distribution, the percent of times where we got a sample mean that low or lower is 8 out of 64, or 12%. It is plausible to get a sample of 68. So I'm saying it is plausible to get a sample of 68 when, or I should say if Hunter did as well as us. And remember, that means that their true mu is 78. So if you're feeling like, oh boy, that's a little complicated, that's normal. Try to push past that feeling. It's normal for this part of this lesson to make you feel like, okay, we just went from 0 to 7 million. The idea behind this is challenging. You'll see it more and more, so hopefully the more you see it, the better you'll feel about it. But essentially what we're saying is, this happened enough in our samples that it is possible that we could get a mean that low from a population that did as well as us. Okay, there's one last thing and then we're truly done. In your Can You Do, it's only 3 problems. It's 1 page, double-sided. It's going to ask you to describe or tell them what one dot on your distribution represents. So I'm just going to go with this dot that I already circled because I thought that he was an outlier. So you'll get, the first question says, we'll say something like, there is 1 dot at 98. What does this dot represent? And what you're going to respond with is the dot, or we can say in this case, this dot represents 1 sample of 5 scores that had an, we can say that slightly differently. Let's say with. This dot represents a sample of 5 scores that had an X bar of 98. So that's not the only way you could say it, but that's a good way to say it. Or you could even say this dot represents one sample of 5 students that had an average of 98. I think I like that one better. I'm going to change mine. You don't have to change yours, but I think I like that one better. This dot represents one sample of 5 students that had an average of 95. That makes more sense to me. So on can you do, sorry, it's not number 1, it's number 3. It's a problem about the height of girls. You can use that sentence frame exactly. Maybe I should have said average score. Score of. Okay, now that's an A+ response right there. I finally got it together. So can you do is in your little baggie. It's at the end of the notes. He doesn't have a staple because it's just one sheet. And I will get solutions up for you before you have to turn this in on Monday. So before you turn in every